Hi, welcome everyone to the seminar. We're going to wait just a few minutes for everyone to enter the room and we'll go ahead and get started momentarily.
Larissa, you're muted.
Sorry, thank you. I'll go ahead and turn it over to you to start the introduction.
Great. Hi, everybody, and welcome to today's seminar on evolutionary studies. It's my great pleasure to introduce to you Anna Reid. Anna is the Executive Director of the National Center for Science Education. She became the Executive Director in 2014. Briefly, the National Center for Science Education, for those of you who don't know, has its mission to ensure that students across the country get the accurate and effective science education they deserve. And they particularly focus on evolution and climate science, which will be the topic of Anne's talk today. Prior to Anne joining the National Center for Science Education, she worked for several years as a research biologist at the Armed Forces Institute of Pathology. And arguably one of the highlights of her career there was sequencing the 1918 flu virus and resurrecting it. And so that's pretty exciting work. She also served as a senior program officer at the National Academies of Sciences for a few years. And then prior to joining NCSE, she was the director of the American Academy of Microbiology. Anne's talk is entitled Changing Minds About Evolution and Climate Change in the Classroom and Beyond. So Anne, we virtually welcome you to Vanderbilt and we look forward to your talk.
Thank you so much. I'm so sorry that I can't be there in person. I've never been to Tennessee and I was really looking forward to it. But as you know, no one is going anywhere right now. At least no one from California is going anywhere now. You may have heard that we have terrible fires out here right now. Until today, the air quality has been miserable. In fact, if this talk had been at the same time last week, I would have been sitting here in the dark with a strange orange glow coming in through the windows because the sun really never came up. But one of the corollaries is the air is very clean today. And so it sounds like all of my neighbors are out working in their yards. So you may hear some chainsaws, some leaf blowers. So I'm sorry about that, but we're all really happy to be able to go outdoors again. So thank you for that introduction. I am going to talk about changing minds about evolution and climate change. Let me just tell you a little bit more about the National Center for Science Education. We aim to make sure that all students learn in their science classrooms what is the best understanding of the scientific community. And that's not a problem with most areas of science, but there are some areas of science that are socially controversial and where teachers may be misleading their students or confusing their students. And so we have 3 interlocking programs. One is to support teachers directly, to provide them with resources that allow them to teach evolution and climate change effectively, even in places where there might not be a lot of community support for it, which is something I suspect many of you are intimately familiar. Secondly, we have an outreach program that aims to increase informal science education about evolution and climate change. We call that Breaking Down Barriers. And finally, we have a program called Catalyzing Action that some of you also might be familiar with, because I know that Glenn Branch, who runs that program, has worked with some of you in the past. When a state or a school system, or even sometimes an individual school is promoting or allowing the inaccurate teaching of evolution or climate change, NCSE will get involved and help the local community fight back against the inaccurate science. So we get involved, for example, when states renew their state science standards to make sure that evolution and climate change are included appropriately. We were involved in the trial, which ended 15 years ago this fall, of Kitzmiller versus Dover, where teachers were asked to teach from an intelligent design textbook. So these three programs work together, we hope, to ensure that these areas of science are treated accurately and that people get a chance to really engage with the evidence for these areas of science and resolve their misconceptions. And you're going to be hearing that word a lot. So why care? Why do we care that these topics are taught properly? There's a lot of reasons, but for evolution, it is the essence of biology. Truly, biology doesn't make sense without evolution. And it has a lot of practical consequences, for example, in designing effective pest control strategies, or treating cancer, treating infectious diseases. So evolution, it's important to understand what it is and what it isn't. Climate change, of course, is the existential challenge of our time, and we are not going to have the political will to deal with it unless people come to accept the science and the urgency. And finally, above and beyond evolution and climate change, we think it's critically important that all students get a chance to develop critical science thinking skills. I think we all see the need for that right now, that being able to evaluate the credibility of news about science is just incredibly important. I'm going to give a couple of examples and then we'll get back to evolution and climate change. So you all may remember this tweet. This is back in March, where President Trump was boosting hydroxychloroquine. And then there were some studies of it. It didn't seem to, it seemed to maybe increase risks. That was from May. This one is from June. Another trial showed no benefits. But then a few days later, some authors retracted that article saying that it was dangerous. And then another study a little bit later said maybe taking hydroxychloroquine actually helps. So, and then a clinical study that it didn't inhibit the virus in preclinical models. So, you know, what are people supposed to think when they get this barrage of article after article after article that seem to be all be saying different things? Another example, more recently, I don't know if you guys came across this, but there was an article, this was from the Washington Post, that said wearing a neck gaiter may be worse than no mask at all. Gaiters are those stretchy tubes that you can pull up over your nose and mouth. Lots of runners use them. And then a few days later, there was another article saying, no, gaiters are fine. And then the original Washington Post reporter then published another story 2 weeks later saying, this is complicated. So back in March, my NCSE's director of teacher support, Lynn Andrews, and I decided that we would put out a weekly coronavirus teachable moment, and we would try to give teachers answers to questions that they might have about the virus, that their students might have, that might come up in class, in a format where they could actually help their students work their way through this kind of science, you know, flood, a tsunami of information. So the Gator one is an example. I wrote this a couple weeks ago. It's called Gatorgate Explained. And what I did was I went back to the original study that all that reporting was based on. And the study is very short and very simple, completely accessible, at least the introduction to high school students, and pointed out that this is what this thing was. It was a proof of principle study. A group of physicists rigged up a way to test how effective masks were, and all that the article was claiming to do was to say, in your, in any average physics lab in a college, you could set up this system and you could evaluate mask types. We're just showing that this thing works. And this is the main graph in the paper, and it shows the testing of all of these different kinds of masks. Those are along the x-axis, and then how many droplets they counted is on the y-axis. So you can see that a properly fitted N95 mask essentially doesn't let any droplets out at all. And then the next one, a surgical mask, also does quite well. And then as you go across all of these different kinds of masks, you get to the end and you get to no mask whatsoever. And that lets a lot of droplets out. And then at the very end is fleece. And that's what they called the gator in their study. And you can see that the fleece appears to have done slightly worse than no mask at all. The other thing and so this kind of exercise to do with a class works on a whole bunch of levels, because one of the science skills that students are expected to learn is how to read a graph. So this is an opportunity to have them really dig into a graph about a topic that they should actually really care about, or at least be familiar with. So the other thing to know about this graph is that the masks where there's an open circle in the reading, those were masks that they tested on 4 subjects. The other masks were only tested on 1 subject. So as I said, this is proof of principle. They're not doing an exhaustive test. They're basically just looking to see, the method that we rigged up, does it work? Can it tell the difference between masks? And the answer is, yes, it can. But does it really tell you anything about how safe they are, or how effective they are at blocking transmission? Only very indirectly. So what were all those headlines about that gators are worse than not wearing a mask? Well, that came from this couple of sentences at the very end of the paper, where the authors said, we noticed in the fleece that we seemed to get more and smaller droplets. Operative word, seemed. And then the conclusion they drew from that is, therefore the use of such a mask might be counterproductive. Operative word, might. And those 2 sentences are what the press picked up on as the exciting thing about this study, that maybe gators are worse than no mask at all. But if you go back to that graph and you look at the size of the error bars on the fleece, I think it's fair to say that this study is not really showing that that a gator is worse than nothing. So this is the kind of thing that a teacher can use to talk to their students about graphing, to talk to them about experimental design, to talk to them about error bars. The error bars are very important here. So we put these teachable moments out every week on a whole bunch of topics. And you're welcome to go to our website, ncse.ngo, and /coronavirus resources. So you can look at them for yourself. They may be useful to some of you in your life, if you're a teacher, or if you're homeschooling your kids and you want to talk about some of these coronavirus topics. You can sign up for a newsletter and get the new ones every week. So I'm going to turn to changing minds in the classroom, which is what I was supposed to be talking about in the first place. So what leads to changing minds? And I'm going to take you on a quick tour of our misconception-based learning approach. Now, the idea here is that when it comes to especially evolution and climate change, there is a lot of misinformation out in the world. Some of it is actually disinformation. It's been disseminated with the express purpose of misleading people. Some of it is just misunderstanding and misinformation. We call, in either case, that students come into the classroom with a misconception. And this work, which is done by John Cook, who's at George Mason University, and many others have also studied this, is that if you want to displace a misconception or a wrong idea, you can't just tell someone it's wrong. That will not automatically make that misconception go away. In fact, in some cases, it can even reinforce it. So what you have to do is replace that misconception with a stickier fact. The misconception is going to be sticky, especially if it's been in your mind for a long time, and especially if it's been told to you by a lot of people you trust. So you can't just leave a vacuum. You've got to replace it with a fact. And then the third step in this process is to go back and have the learner identify what the fallacy was behind that misconception or that myth. John has developed a framework called FLICK that divides the different kinds of rhetorical tricks into these 5 different categories. So I'm going to give you an example. This is from one of our climate change lessons. The fact is that recent climate change is not like past climate change. The myth, though, is that the current climate change is just like past change. And you'll hear this all the time. Oh, climate's always changing. That's no big deal. And then we'll see that the fallacy involved in that myth is jumping to conclusions or the single cause fallacy. So now I'm going to try to exercise my Zoom Zen master skills and take you to a website. So let's see if I can remember how to do this. New share. All right, let's see if this works. All right, I hope you're seeing a website here. I hope you can see my cursor moving around. And I'm going to launch this visualization. So this is what a teacher would do in the class on this topic. You open up this website and you can see that you've got a volume scale on the y-axis. The x-axis is time, and it is 800,000 years of website data, of ice core data. And these are the changes in temperature indicated by the ice core. You can also graph the carbon dioxide, N2O, and methane. So for right now, we're just going to look at CO2. And gosh, it sure does look like it's just been going up and down over time. What's the big difference? Well, here's what the students can do that I think is just super cool. And this really engages them in the evidence. So you can blow up any part of this graph. And you can challenge the students to say, okay, find the time when CO2 has been changing the fastest. And so they can go in here and they can measure any little part of that graph and it will give them the slope. So you can see the slope here is 0.012. And you can challenge them to do this anywhere in the graph. They can pick an area. They can find a fast plate where that looks really fast, like that looks like a good one. Let's do that. Here to here.
Hi, Ann. Sorry to jump in. We cannot see, all we see is the front of the website. We cannot see the one graph that you're focusing on. So
okay, let me see if I can fix that. Now can you see it?
Yes.
Oh, I'm so sorry. Okay. So now you can actually see what you've only been able to see in your mind. Here is the actual graph. Here is the little place where we measured the slope, and now the slope is 0.04. So they found a place that's fast, where it's been rising faster. Now let's go to the present. You can zoom in on the last 5,000 years. And now you can, let's start, that's 1765. Let's go to 1854. And then let's go up here to 2014. Now the slope is 0.7. You can see that it's more than 10-fold faster than any time that they would be able to find in the past. So this is very powerful because you can actually see where the misconception comes from, that it certainly does look like that carbon dioxide has just been going up and down. But when you actually dig in, you can see that the changes are very, very different now. And that's a way to replace that sticky misconception with a stickier fact. I'm going to try to go back to the slideshow now. And hopefully even to the same place we were before. Antonis, can you confirm that we're back where we're supposed to be?
We see the presenter view now, not the one slide.
Okay. Sorry about that, folks. How about now?
Yeah, that works. Thank you.
Okay, so this is where the correcting the fallacy comes in. And John Cook, who we were just talking about, has this, now I'm not able to click forward there. Okay. He has developed a whole series of cartoons that illustrate these fallacies. So the jumping to conclusions fallacy, this is a logical fallacy, is just because the climate has changed in the past doesn't mean that all climate change is the same. So the cartoon shows John's character, whose name is Cranky Uncle. He's falling through the air and nothing bad has happened yet, so clearly nothing bad is going to happen. And this is his cartoon for the single cause fallacy. You can see that Cranky Uncle is making the assumption that this person died of natural causes because people have always died of natural causes. That's the same situation as saying the climate changed in the past, and that seems to have been okay, and so current climate change is not a problem either. John is quite a remarkable person. I really encourage you to check out his YouTube channel. He has a series of short videos illustrating various logical fallacies, both about climate change and lately about coronavirus. They're excellent. Up in the top right, you can see his book, which is called Cranky Uncle versus Climate Change, and that's available at Amazon. And it's also a premium if you join NCSE. So not to toot our own horn too much, but if you want to get a really fun cartoon book about climate change and support NCSE at the same time, you can. Okay, so I'm just going to go through very quickly. We have 3 sets of lessons that teachers can use in their classrooms that are all based on this misconception-based learning concept. The climate change lessons are already available on our website. The 5 lessons cover these 5 important facts about climate change. And they have been carefully designed to counter the most common misconceptions about climate change. Now, I'm showing you the facts first and the misconceptions second, because that is, it is important not to reinforce the misconceptions by repeating them without saying they're misconceptions. So these are the sticky facts that we want the students to end up with. And these are the misconceptions. And I think you'll recognize these, that, you know, scientists don't really know whether it's changing or not. Models are not reliable. Extreme weather can't be attributed to climate change. There's nothing we can do about it. I'm sure you've heard all of these. You may have your very own cranky uncle who believes these myths. But we can show that students who have experienced these lessons are much less likely to still hold these misconceptions. And I should say that for NCSE, it's important to us that teachers recognize that it's not necessarily going to be enough just to give your students accurate information. Because if they have come in with these misconceptions, they might learn the facts that you tell them, they might repeat them on a test, but they won't necessarily believe them. And they definitely might go out of the class with those sticky myths still being at the forefront of their mind. So this approach is very intentional to try to make sure students have an opportunity to undo those misconceptions on their own by examining the evidence. We are currently rolling out a set of lessons on the nature of science. This was in response to the coronavirus pandemic. In the spring, we decided we needed to boost our schedule and get these nature of science lessons done, because we know that teachers have a real opportunity now at the beginning of the year to teach the nature of science. All of these lessons are designed around epidemiology and the coronavirus, and so they're very, very current, and they should be things that the students really can engage with. And then in the spring, our evolution lessons will come out, and you can see the myths that those lessons are going to address. So we're really excited about those. But I did say beyond the, in the classroom and beyond. So I want to talk a little bit about what effective engagement looks like in the wider community, where many of you may want to be making a difference for science communication and science outreach. So first, we're going to take a little look at what effective engagement doesn't look like. There we go.
My reasons for marrying are, first, that I think it a right thing for every clergyman to set the example of matrimony in his parish. Secondly, that I am convinced it will add very greatly to my happiness. And thirdly, which perhaps I should have mentioned first, that it is the particular recommendation of my noble patroness, Lady Catherine de Bourgh. Mr. Collins, she said, you must marry. Choose properly, she said. Choose a gentlewoman for my sake, and for your own, let her be an active, useful sort of person, not brought up too high. Find such a woman as soon as you can, bring her to Hunsford, and I will visit her. And your wit and vivacity, I think, must be acceptable to her, when tempered with the silence and respect which her rank will inevitably excite. Yes. So much for my general intention in favor of matrimony. Now, as to my particular choice. My dear cousin, being as I am to inherit all this estate after the death of your father, I could not satisfy myself without resolving to choose a wife from among his daughters. And now, nothing remains but to assure you in the most animated language of the violence of my affections.
Mr. Collins, please.
To fortune.
I think we can all agree that that was not an effective engagement between Mr. Collins and Elizabeth Bennet. I think that actor is absolutely brilliant. The point that well, if we were in person, I would be asking you to raise your hands if you would have accepted, but I can't do that on Zoom. But I'm going to assume that you would recognize that none of these qualities of effective engagement were on display there. Respect your audience and build trust, not so much. He didn't ask any questions. He didn't establish any common values. He didn't, in fact, engage at all. And if we'd continued with the clip, you would see that even when she objects, he refuses to listen to her. It's funny, that clip, but I'm afraid that an awful lot of scientists come off that way, as just really pompous, really know-it-all. You don't know anything and I know everything, so let me just explain to you and then you will be enlightened like I am. So it's a little bit of a cautionary tale that when you set out to do science engagement, that maybe you think back to that clip and think, I really don't want to come off that way. So how do you want to come off? It's really important to ask questions. Don't assume that you know what the person thinks or what the person cares about or how much they understand about the science. Ask, ask, ask. Do less talking, more asking. Now, when it comes to topics like evolution and climate change, it's important to have some idea of what your audience might be thinking. For example, when it comes to climate change, this is a map out of the Yale Climate Communication Lab. They have fantastic interactive resources that you can look at. This is acceptance of climate change by county. And the oranger the county is, the more above the national average the area is with respect to accepting climate change, the population is. The bluer it is, the farther below the average national acceptance the community is. So you can see that the part of the country where you are, acceptance of climate change is generally below the national average. So where you are matters. That's going to affect who you're likely to come across in your audience. Climate change acceptance is deeply polarized politically, and this is from 2016, but I think that the numbers have only gotten worse, that liberal Democrats are the most likely to accept climate change, conservative Republicans are the least likely. And this, I think what's important to know about this is this is a much better correlation with climate change acceptance than actual knowledge. So liberal Democrats who don't know anything about the science of climate change nevertheless accept it, and conservative Republicans who might know quite a lot about science don't accept it. So that's important to know where the resistance is coming from, and that gets to the values part of the conversation, which we'll get to. On the other hand, there is a lot more shared ground than people might than you might realize from looking at those numbers about the polarization, which is that most adults do say that climate change affects their local area, and a solid third say it affects them personally. So that's a space for common ground. Furthermore, there's a majority of both Republicans and Democrats who support the increased use of solar energy and wind power and alternatives to fossil fuels. So again, there is some shared ground. And that's where you're going to be the most likely to be able to start having some effective engagement. So as I said, ask questions, establish common values. And one way to do this is to intentionally get to know the person, get to know about their family, get to know about where they grew up, what they care about, what is their favorite place that they go hiking or swimming or boating or hunting. Ask them what they think about schools and what's the one thing they might change about schools if they had the power. Ask them what books they read or what movies they love. Just get to know the person and start to find out what you might have in common. And then science is all about observation, whether it's observing the natural world, observing what happens in an experiment, observing what happens when you change the parameters of a model. And so this is something that you can model in your outreach and in your conversations about science with people. So take, for example, the idea of you find out that the person grew up in the Smoky Mountains. Oh, what did you like to do there? Did you like to go for hikes? I remember I grew up in Cincinnati, and I remember when the May apples bloomed in the spring, and then I knew, that it was spring. And I so distinctly remember finding those amazing plants and being so excited about it. Tell stories like that, inspire the person to give you stories back, the observations that they have made in their life. Then you can get to things that may be a little bit, may seem a little bit touchier, but won't be after a conversation like that. What changes have you seen in the local weather in your lifetime? Or maybe, have you ever talked to your grandparents about what this was like when they were kids? What the area was like? What kinds of changes have they seen? And there have been changes. There have been changes everywhere. So you're going to start putting together in their heads some things that they believe that they have kept separate, perhaps, from whether they accept or don't accept climate change. And then if you can, it's nice to offer opportunities to engage with actual evidence. One of the things that I love to use, because so many people are interested in gardening or at least just taking care of their yard. is this map. So if any of you are gardeners, you've probably seen this map or a more recent iteration. This divides the United States into gardening zones that tell you what you can plant in different places. So the deep purple at the top is hardiness zone 3. You are not probably going to be able to grow bananas there. And then down at the very bottom, you can see just at the very tip of Florida, there's some zone 10 where you probably can grow bananas. And then you've got everything in between. So I'm going to morph this map into the 2006 version. And the best way to appreciate the changes, I think, is to pick a place. Like you could pick Tennessee. And you can see that it's about half and half zone 6 and zone 7. Or you could pick another area. You could pick, for example, I spent many, many summers in Vermont. You can see here that Vermont is mostly zone 4 with a little bit of zone 3 at the top. Okay, ready? We'll go back and forth a couple of times. So you can see now Tennessee is completely 7. There's practically no zone 6 left. And then you can see here, I'll do it again. Let's go back. There's 1990, pick a spot or pick a color and look at what happens. So again, if you look at Vermont up here, remember in 1990, it was almost entirely 4, and now it's almost entirely 5. So what does that matter? Well, sugar maples are not real happy in zone 5. They're a zone 4 plant. And so maple syrup, which is a staple of Vermont and an important part of its economy, is the sugar maples are going to be struggling. And if this continues, they might not be able to produce in Vermont at all. And that's true across all of these areas. If you think about, let's go back one more time. Let's look at Iowa here. Mostly 4, a little bit of 5. Now it's all 5. Well, I don't know for sure, but I can't imagine that corn and wheat and soy don't do differently when the temperatures get consistently higher. The growing season gets longer. The first frost comes later. Some of them might do better. In many cases, there are strains of those agricultural crops that are bred to do well in other climatic conditions. But the point is, in 16 years, this map has really changed dramatically. And this is a great place to start a conversation with someone about changes in the climate. But the point being, though, that first you build the trust, first you get across to the person that you are actually interested in what they think and what they care about, that it's not a fight. It's not an argument that one of you is going to win and the other one is going to lose. It's a conversation, and it's a process. This all doesn't happen in one conversation. It takes a while for someone to change their mind. There's a wonderful story that Catherine Hayhoe tells. She's a climate scientist in West Texas, that she's been working with local farmers to install wind turbines on their farms. And these are generally very conservative people and generally very, very distrustful of science in general and climate science in particular, but they like saving money. And so they like putting these wind turbines up and using them to power their farms or sell energy back to their communities. And she said she doesn't even talk to them about climate change early on. She just talks to them about the savings and the efficiency. And she finds that once they trust her and once they're saving some money, a little part of them opens up to the idea of learning more about what's going on. And so you just have to see it as a long-term process because sometimes it takes a while to change people's minds. Oh, where's my cursor to start this? I wanted you to know that Elizabeth ended up happy, but maybe I'll just have to tell you the story. So you saw her first engagement, engagement proposal, which she refused. She was then proposed to by this man in an extremely supercilious and condescending way that also didn't respect all of my rules for effective engagement. But at the end, he comes back, he says he was wrong. She says she shouldn't have judged him so quickly. And there, they finally had an effective engagement. So can we change how everyone thinks about science? I think we would all agree that it's never been more important to help everybody around us come to have the confidence of evaluating scientific evidence that you might have. And I hope that you've taken something home from this talk that will help you talk to people like that, because I think absolutely we can change how everyone thinks about science. And if you'd like to help NCSE with that, I encourage you to join us. Even if you don't become a member, I think you'll find a lot of really terrific information on our website that will help you with outreach as well. And I do want to say thank you to all of the people who work at NCSE. Many of you may have met Glenn last year when he came out and spoke in the same series. And then this is it. This small group of people is trying to transform how evolution and climate change are taught. So we need your help. We would welcome you joining our organization and getting our newsletter and following us. And of course, if anything ever happens in your community that you're concerned about, please let us know, because we are ready and willing to come in and help you resolve any kind of issues that might be happening in your schools or in your state house or on your state board of education. So I look forward to having some time for discussion. So Dr. Rokas, I think you're going to moderate the conversation.
That's correct. Thank you for a wonderful talk. So yes, please enter any questions you have in the question and answer box, and we'll start addressing them. We already have one question from Jamie Camp on how do we access the zone changes, and whether that's on the website of the National Center for Science Education.
It is not. I will get the website and post it. It's the USDA is the organization that generates those maps. So the current one would be at the USDA website. But if you just Google zone hardiness maps, you'll pull up and ask for images. You'll find some of the older ones as well.
Perfect.
It's a good idea to put it on our website, though.
It's unbelievable how quickly in 15 years how Tennessee changed completely.
Yeah, it's very. Yeah.
And that gives me an excuse for being a horrible gardener, is that, you know, it's not me, it's the climate that's changing.
Absolutely. I'm sure both of your thumbs are green.
I had a question about, you mentioned this in the context of climate change, that with one of the scientists you referred to, that she doesn't talk about climate change, she just engages in conversation. And right, the same thing could be said about evolution. I wonder if you have strategies, right? Very often we hear about the use of the E word, right? That a lot of the effective communicators of evolution that I know sort of try to avoid, at least early on, talking explicitly or using the word evolution. They just talk about the evidence, they talk about the science, and you know, then maybe at the end say, and that's evolution. But sort of avoid it in the beginning, precisely perhaps to avoid that. So I was wondering if you had any thoughts on that.
I think that's absolutely the case, and teachers generally don't lead off, well, the effective teachers, I should say, don't lead off with, okay, today we're going to cover evolution, get ready, you know, strap in. Instead, they do exactly what you're saying. And in fact, the next generation science standards that are now being used in 20 states and standards very similar to them are used in 24 states, they actually start bringing in concepts that are important to evolution as early as kindergarten, so that kindergartners would go out into their schoolyard and observe what kinds of plants and animals live there, and perhaps start to observe some of the relationships between those plants and animals. They might see ants in a certain area. They might see bees on a certain flower. They might see squirrels up in the trees, so that they start getting the idea that organisms interact with each other and with the environment. It's a very foundational concept for understanding how evolution works. And then it builds on that, so that by the time they get to, say, 9th grade intro bio, they already have all the building blocks that you can start putting together to say, this is how species change over time. And then exactly, I mean, in an area where the evolution word itself is triggering, you can wait until the very end of the year and say, and that's evolution, that's all it is. You know, you might have had all of these, you know, terrible ideas in your head of what it means, and that's it. And now you know all the evidence for it, and you know how scientists know what they know, and it's not as scary. Yeah, there are some states that don't use the word evolution in their state science standards for exactly that reason. So it is still, it can still be very sensitive. In just general conversation with people where you don't have time to do that kind of slow build, I think most of you have probably talked about antibiotic resistance with people. And again, you don't have to call it evolution, but it's such a clear example of selective pressure that people get. In my introduction, you mentioned that I worked on the 1918 influenza virus for many, many years, and it evolved. And of course, influenza viruses continue to evolve. And 2 weeks ago, I got a call from a journalist saying, I have to write this article about what happened to the 1918 flu, and will the same thing happen to the coronavirus? And he said, so the 1918 flu went away. Is that going to happen with coronavirus? And I said, what do you mean it went away? It never went away. It's still, 5 of its gene segments are still make up our current influenza virus. It evolved. And it sort of blew his mind. But you know, viruses, also coronavirus, is a great opportunity to talk about evolution. A concrete example that people can relate to is the best entry point.
Thank you. We have another question from Abigail Labella, and she asks, you spoke a little bit about mistrust in science. Even when it comes to climate change, I have heard adults say that scientists fabricate data or show only data that proves their point. How do we respond to challenges of the data itself? What would your suggestions be?
Oh, Abigail, that's a good one. Yeah, and a sort of corollary of that is maybe a slightly more sophisticated one, is that scientists cook their conclusions because they know they won't get grants unless they come to the conclusion that that the man wants them to come to. And you know, that is, if someone is really committed to that idea that scientists don't tell the truth, you're going to have to rewind way back to overcome it. You're not going to be able to just, you know, drop a bunch of facts on them and get them to change their minds. So I think I would go to, you know, why do you think scientists would do that? And do you think all scientists do that all the time? And then maybe get into how do you think science changes over time? How do we learn things over time? You know, that, and try to help the person start to see that if everything was made up and scientists just said whatever they thought people wanted to hear, you would never get anywhere. Science would never advance in any way. It would always be completely random. And yet we see evidence all over the place that science does actually accumulate, and we get so that we know more and more about things. So that would be, you know, my advice. If you run into someone who's really dug in a very negative way, then it just means that you've got to really get back to basics and build some trust so that you can start having those more meaningful conversations.
Thank you. Another question I had was, you know, as practicing scientists and you know, members of academia, how can we help the National Center for Science Education how we can engage, right? So we live in a world where I think more and more of us realize that we need to be active participants to changing the world and improving education and get out of our bubbles. And so what would your suggestions be for especially folks that are starting to engage in outreach, or that are at the beginnings of their careers and they're wondering, you know, how their skill set is a good fit, you know, how to use their skill set for outreach and for helping in these causes?
It's a great question because I think that a lot of, especially young scientists, really feel a responsibility to have a broader impact with their science, and that's fantastic. But I think it's a little bit counterintuitive that almost always when scientists think about outreach, they think about visiting a school and going into a classroom and you know, sort of being a model, a role model. And I'm not saying that that's not important, but it's very limiting. And it also tends to be unsustainable. You know, a lot of scientists will do that when their kids are little and then they stop when their kids get older. That certainly was the case with me. It also ends up that all of the graduate students at your university end up going to the same school when there are, you know, maybe 5 or 6 school districts nearby, and some of them are not getting anybody visiting them. So we actually have something we call a graduate student outreach fellowship. It's a very, very small program right now, but we take graduate students and they basically do a year-long course where they learn how to evaluate what kind of science is available in their community, what the community is like, what people are interested in. They learn how to design an effective activity, and they learn how to talk to people in a way that's effective. They also learn some practical skills like grant writing and how to get an IRB approval to do an informal science outreach research project. We will probably not have another cohort of those students until next year because it's not a very good time to be training people in outreach when you can't, you know, interact with other people. So that's a little bit on hold, but we do have a lot of information about all those things on our website. But I think thinking much bigger than that, this kind of conversation that you can have with the parents on your kids' soccer team, with the people at your church, with your neighbors, where you open the door to asking questions in a way that helps all of these people in your world see how scientists think and see how scientists engage with other people in a way that's respectful and really interested in learning from them rather than just lecturing to them. Our model for learning science often is very top-down, very hierarchical, that you go into a class, the professor gives you the information, you assimilate it, you spit it back. That was science learning. And we tend to take that mental model into our community interactions. And what I'm really encouraging is this kind of, where can I find a way to bring science into my conversations with people in my community in a way that they will be excited about science instead of either intimidated by it or distrustful of it.
Great, thank you. We have another question from Julia Miller. I'm troubled by what I'm hearing about people being persuaded by wild conspiracy theories. Would you approach those conversations in the same way as you described? Or would you have any specific suggestions for talking to people enamored by conspiracy theories?
Yeah, the conspiracy thinking is really taking off like a rocket right now. And it is, I agree, a big concern. I would steer you back to John Cook, who I mentioned, he developed that FLIC rubric for evaluating fallacies, rhetorical fallacies. He has also developed a rubric that is called Conspire, and each of those, each of the letters stand for some aspect of conspiratorial thinking. He has a series of very short, like 2-3 minute videos that explain these various aspects of the thinking. And it's really helpful to kind of break down what is it that makes something conspiracy thinking versus some other kind of thinking. One example is that there can't be any evidence that the conspiracy is incorrect is evidence of the conspiracy. So if you say, you know, we actually, you know, that pizza parlor in Washington, D.C. doesn't even have a basement, and the person says, I bet there really is a basement and they're not telling us, then you're like, well, how can this thing even be, disproved if even evidence that it isn't true, you reject as. So you see where I'm going with that, that I think if you start becoming really familiar with the sort of the specifically what differentiates conspiratorial thinking from clear thinking, then you might have an opportunity, if you're talking to somebody who believes one of these conspiracy theories, to say, it sounds to me like nothing can disprove this to you. What kind of evidence could there be that would make you maybe wonder whether this is real or not? Just to pick that one example of one of the ways of thinking about it. I'll tell you, engaging on Twitter is not the way you're going to change anybody's mind about a conspiracy theory. This is going to have to be, individual to individual.
Thank you so much. One more question from Kate Snyder. Much of science outreach and education in K through 12 seems to be fact-based, giving students interesting tidbits to pick their interest or memorization of facts. A result of this is that science has become synonymous with facts, and when science comes out with a new finding, it gets interpreted and reported as a new fact. Teaching the scientific method doesn't actually combat this directly. Do we neglect the teaching of scientific consensus? Paradoxically, teaching the uncertainty of a given topic seems to make the uncertainty the sticky part of the message. Any ideas on how we can promote tolerance, acceptance of uncertainty while not undermining the message that science is the best we have to figure out reality?
Yeah, it's a fantastic question, Kate, and you're exactly right that it's the balance between science is never done, it's never sure, it can always change, and science knows nothing. My personal frustration in that particular area is nutrition research, because people are really interested in food and in drink and in when they want to eat things that are good for them. So they really follow nutrition news, but it tends to be broccoli's great for you. Don't eat too much broccoli. 1 glass of wine a day is good. No wine at all. Meat's good, meat's bad. And they're like, scientists don't know what they're talking about. And so you're right that it's a real problem. I with that one in particular, I will often ask people to say, okay, yeah, nutrition is hard. Let's think together about how we would design a study to show whether or not broccoli is good for you. And once you really start thinking about how would you design that study, I think most people will quickly realize that it's really hard. And therefore that any individual study that they see needs to be taken with a grain of salt, not because it is just bogus, but because it's hard to get a signal in such a noisy system. What you said about how it's taught, I really hope is changing. And we at NCSE are working really hard to encourage the best kind of science teaching, which is what is expected under the next generation science standards, which is entirely inquiry-based instead of fact-based. The students learn a lot of facts because if you have to defend your interpretation of the evidence, you may have to go out and learn a bunch of facts to be able to back yourself up. Those facts will stick because you've gone out and learned them for yourself for something that you needed to do. So that example of playing with that climate model is an example of a more effective science pedagogy that is expected more and more. And as the next generation science standards are implemented, you'll see more and more of that inquiry-based learning and problem-based learning.
And then final question from Larissa. The public is fascinated with fossils and must have owned a toy dinosaur. How do we capture the initial interest and point out what evolution is and how it relates to deep time to the youngest citizens and their parents?
Yeah, that's a great question too. Our evolution lessons are going to focus even on human evolution, which is also something it's sort of the third rail of evolution in terms of people's acceptance, but it's also the area that people are automatically, kids especially, are really interested in, of you know, where did we come from? Where did humans come from? But the dinosaur thing, I don't know about you, but the whole birds are dinosaurs discovery that has happened over the course of my own lifetime, this realization that the dinosaurs actually survived in the form of birds, is just super compelling to me. And I don't think that you could show a kid a wild turkey and not have them see the dinosaur in it. They are terrifying if you've ever been up close to a wild turkey, at least to me. I mean, maybe I'm a little wimpy, but I've been chased by them when I'm on my bike, and they're big and they really look like dinosaurs. So I think getting students really thinking about, yeah, dinosaurs are really cool and they're still here is maybe a way to really bridge that, that sort of interest in a toy to connect it to the real world.
Oh, that's perfect. That's the perfect conclusion to a wonderful seminar. So thank you so much. I encourage those of you who want to talk more with Anne to join us for the Zoom reception in a few minutes. But without further ado, thank you so much for a wonderful seminar, and everybody have a good evening. Bye.
Thank you so much. And the link to the Zoom meeting is in the chat box.